Let's go over a couple exceptions to the octet rule. Some of these you're going to need to memorize, other ones are going to be things you come up across when you're just drawing your Lewis structures. So the first exception to the octet rule is boron. So boron, due to its electron configuration, has less ability to attract electrons, and therefore it can't fill up a full octet. It is completely satisfied with only 6 valence electrons. So unlike most other atoms that want to meet the octet, this guy only needs to meet a septet, okay, or sextet. It only needs 6 valence electrons. You just got to remember that then when you're drawing the Lewis structures. Then there is the expanded octet. So once we get to elements in periods 3 through 7, so we get to larger atoms, which means they're going to have more protons, so more ability to attract, and they're also going to have larger shells. Those larger shells, it's not just going to be S and P, they're going to have S, P, and D in their outer shells. And so that means that they can accept more electrons than just the typical 8. You know, S is 2, P is 6, and if you throw the D in there, really that's 16 valence electrons that they can technically hold out there. And while they'll never get to 16, you're going to get to higher than 8 sometimes. And you recognize this because you follow the steps for drawing Lewis structures. Alright, here's an example. Phosphorus pentachloride. So we looked at phosphorus trichloride when we talked about Lewis structures, and in phosphorus trichloride we just had 3 chlorides bonded to phosphorus. And what was happening there was, if you look at the electron configuration for phosphorus, it has 3s2, 3p3. That means it has room for 3 more valence electrons in its p orbital. So if we look at the 3p, phosphorus had 3 valence electrons in there. And what happened when we did phosphorus trichloride? Well, those chlorine atoms, they came in and they shared one of their electrons, and there was your 3 bonds. So if it's just this little section right here, we have all of those covalent bonds represented as just a sharing of electrons. What can happen, though, is since phosphorus is big and there's technically a 3D shell hidden inside with those 3Ps, it's just usually not filled until 4s is. But the 3D sublevel, some electrons can be promoted up there. And so as a result, phosphorus can share some other electrons in the 3D. Alright, so here's 2 electrons that phosphorus bumped up to the 3D, and then the other 2 chlorines are going to come in and share their electrons. So that would be these 2 bonds right there represented like that. Now it's a little more complicated than that. It's not actually 3D. We'll talk about hybrid orbitals later and how this takes place, how it is that electrons are promoted. But just be aware that you can have expanded octets, and you have to recognize them because you follow the steps for drawing Lewis structures. Same thing with sulfur. Sulfur normally had just room for 2 more electrons in its 3p shell, but it'll upgrade its 3d shell, and it'll share electrons with more fluorines, and we end up with SF6. And it's not always bonds. Here we look at xenon. Xenon has 4 bonds, so that's 8 valence electrons, and then it has 2 lone pairs on it, so a total of 10, 12 valence electrons surrounding xenon. Once again, if you follow the steps for Lewis structures, drawing molecules like this, there's no trick to it.